welcome and thank you for this invitation and thank you for being here. So imagine you're taking a walk through the city of Linz and you eventually crossing the bridge, the Nibelungen Bridge, across the river Danube, and in the middle of the bridge you stop and look into the Danube. You will most probably see something like this. So we see there's a fast-moving region of water, and just behind the pillar there is even backflow of there. But a part of this, it's a rather irregular motion. And in the next couple of slides, I would like to give you a second look on it. So I now have snapshots of this movie. So there's this fast-moving region, and there's the slow-moving or even backward oriented motion, and in between you have a shear layer. And in this shear layer, inside this shear layer, I highlighted so discrete dots, which are actually vortices. So they are rotating vortices. And if we proceed, so the next slide, we see that these vortices are moving together with the flow. And if you focus on the upper vortex, this one is taking up momentum, while this one is losing momentum, and eventually the next one is approaching from below. And so we have some characteristic flow pattern in this type of flow. And at this point, let's make a thought experiment. Imagine you're standing there on the bridge and you have a basket of white color, and you're throwing in the white color into the Danube. So this is a thought experiment. You don't do this. And only the color, not the basket. And so in the next instance of time, this white color will be affected by the flow, and maybe this is a sketch. This will look like this. So we see that the color moves, the dot moves, and there's dilution. And obviously, this shape is somehow influenced by this vortex. Actually, we can decompose this motion into one motion of the midpoint, which we call convection, and the dilution of the color. So it's becoming more and more transparent. This we call diffusion. So if we are interested in this phenomenon of pollution transport, we can rely on the governing equations of fluid flow, which were derived by these guys, Navier and Stokes. So more than 150 years ago, they came up with these equations. But still, despite their age, we cannot solve them, at least analytically. So what we typically do is we apply a computational grid like this, and then we can transform these complex equations into a huge set of very simple equations for each of these small volumes here, and solve them in an approximate way. The drawback is that we need many of those small volumes, so typically 1 million to give you a number, and that it takes time to compute in the end. So we need, let's say, 1 day for a dispersion process which lasts only a couple of seconds or minutes. So at this point, let's make just another thought experiment. So imagine you're standing on a bridge, you're looking into the river, and you're making snapshots of the flow, and you're able to memorize all those snapshots. So actually, this is now in your brain. So, and now you could start from the first frame and replay until you reach this frame here. Then suddenly you have a feeling that you have seen this again, already seen this. And actually, you're wrong, because it's not the same, but it's similar. So, and you might argue that it's not too important if the vortex is now situated like here or here. So in both cases, the vortex will disperse the white color in some way, in some similar way. So you might argue that you might proceed with this slide. So you have jumped from this slide to this slide. Now you might proceed with this slide, and eventually you find other pairs of snapshots which have some degree of similarity so that you can jump. So in the bottom line of this slide, we could say that despite the fact that this database is restricted, we could evolve a flow out of it which goes beyond the time span of the monitoring. And if we accept this procedure, then we don't have to solve for the flow anymore. We just have to solve for the dispersion of the white color. And as a consequence, the simulation time drops from 1 day to 15 minutes. Yet we could look at the same situation from just a completely different perspective. So we could assume this computational grid as a system or a network of nodes which are connected somehow. So we replace these two guys by this lady and say, okay, this is a lady from an early age of telephone, and if we throw in the white color into this network, we activate this cell. So in the next time step, this cell just calls its connected cells. So this would mimic convection. And then the receiving cell just shares that information with its neighboring cells. This would then be diffusion. So this cell shift and phase swap is probably the easiest way to model convection and diffusion in pollution transport. And if we follow this strategy, then we don't have to solve for any equation, because these connectivities are already part of our database we have established beforehand. So in this case, we could further drop the simulation time to 10 seconds, so from 1 day down to 10 seconds in the end. So 4 orders of magnitude faster. So in our LRT project, we would like to focus on this methodology and apply it and further develop it for pollution transport in air, so in the atmosphere. So we switch from water to air. And in the first period of our project, we tested it with this benchmark experiment. It's a very old benchmark experiment. There is a cube situated in a wind tunnel, and on top of the cube, a gas is introduced. And in the wake of the cube, the concentration of the gas is measured. So this has evolved into a very prominent validation benchmark with lots of scientific papers around it. So this is a trustworthy validation base. So in the next slide, you see on the top animation the result of full equation-based CFD, and on the bottom simulation, the results of fully data-based simulations. And the corresponding simulations time dropped from 86 hours to just 7 seconds. And on the left-hand side, you see a validation study my colleague Yasin Du performed, and also the quantitative comparison shows really convincing agreement between simulation results and experiment. So in the future, we would like to use this methodology in order to study traffic-induced pollution. So traffic-induced pollution is pollution caused by driving cars on a street, and a typical street can be considered as a line source of pollutants. If you, however, encapsulate this street by a tunnel, then this line source transforms into a point source. And actually, the point source is of high concentration, because all this concentration along the lines are collected into one point. And actually, this is the situation we will have in Linz. So I just placed this sketch here at the portal of the future West Ring tunnel. So we will have a high pollution source just in front of the Wissensturm. And I'm interested in and would like to investigate of how this pollution source, point source, influences the residential areas in the wake of the Wissensturm. We would like to investigate this by high-resolution simulations, and on top of this, we would like to perform the high-resolution simulations in real time. So we would like to have the results as the concentration evolves in reality. This is actually my last slide. I thank you for your attention, and I'm happy to take the questions.